product integral and product derivative. Okay, so in this video we will discuss on what this thing means, what does it mean to have dx in the exponent, and what this kind of differentiation means. Okay, so before we go to that, it's essential to know about normal integral, that is Riemann sum integral, which is something like this. This is a sum from I equals to 1 to n of f of a, if this is from a to b, a plus b minus a by n times I times b minus a by n, and if limit n goes to infinity, this Riemann sum will go to integral. This Riemann sum will be equals to integral. Here b minus a by n is actually delta x, that is the length of a subdivision while we are integrating, and this is actually a plus I times delta x, so that's just xi. So this is actually equals to limit n tends to infinity of sum from I equals to 1 to n f of xi times delta x. So this is the normal integral. And sometimes in mathematics, out of curiosity, we just want to try new things, and yeah, we just want to try new things and invent new things. So in that process of invention, we also thought of why not, if the continuous summation gives us this Riemann integral, we can also define a continuous product and let that be a new kind of integral. So with that prospect in mind, we defined a new kind of integral, which is actually a product and not a sum. Now, if sum is going to product, product will go to exponent, and the reason is product was a repeated sum. Now exponent is a repeated multiplication. So this product of f of xi and delta x will go to exponent, and when limit n tends to infinity. So now for this expression, we begin calling this as a product integral, where we have, okay, f of x to the power dx. Okay, so we made this definition. But now, how do we evaluate any product integral such as integral from a to b of x to the power dx? How do we evaluate this? This is a problem. But don't worry. This can in fact be changed as a product or a Riemann integral as well. We can change this in Riemann integral. Let's say if we take log on both sides. If we take log on both sides, we can change this to a sum from the product. We will have limit n tends to infinity of, this will be sum from I equals to 1 to n of delta x ln of f of xi. Yeah, if you take log on both sides, products will change to sum and the power will come as product. So this is what happens. Now, sum function times delta x, when it's being summed, that will be a Riemann integral, and this integral will be integral from a to b of ln f of x dx, and this is actually ln of, okay, this is not over here, it's in the exponent, ln of integral from a to b of f of x to the power dx. Okay, so now this gives us the idea how we can calculate a product integral. The ln of product integral is equals to integral of ln of Riemann's integral. Yeah, and for that, now we can finally write a formula for product integral. That's integral from a to b f of x to the power dx is equals to e to the power integral of ln of f of x, and this is a Riemann integral. Yeah, okay, so this is a good formula. Now we have a new kind of integral, that is product integral, and we even have a way to find the product integral. And now it may not be kind of obvious the interpretations or applications of this integral right now, but in the future, in some time, there might be some cases where we might need a product integral or a product of many terms, and at that time we may find the use. And of course, there has already been many interpretations in measure theory and so on. So this product integral, which was invented out of curiosity, like just for the sake of fun, and now we also have a way to calculate this product integral, and this turns out to be useful. So this turns out that it can have use in many fields, and we can also evaluate this. Yeah, so this is kind of way of inventing maths as well. Now if we want to evaluate this integral, it will be just e to the power integral of ln x, yeah, dx, and so that will be e to the power x ln x minus x, and that is it. So and we have limits, you can evaluate that definitely. So this is the product integral of x to the power dx. Now we can also try some other product integrals for the sake of practice. So let's say we want to find the product integral of e to the power x, yeah, and those to the power whole dx. Now that will just be e to the power integral of ln of e to the power x dx. And now that will be e to the power integral of x dx. So product integral of e to the power x is e to the power x squared by 2. Let's try another as well. Let's try integral of, let's say, let's try for now a to the power x. Let's say let's try a to the power x. Let's just try for a constant value c. Let's see what does that uh, uh, solve to. So now this will be e to the power integral of ln of k dx. Now this is a constant, so we will have e to the power x ln of k. Now if we take integral of 1 to the power dx, that will be e to the power integral of ln of 1. Now ln of 1 is 0, so this integral will just be 0, so that's 1. You see, for 1 the integral is just 1, so the derivative of 1, okay, now this is not the product derivative, so the inverse of product integral is just product derivative. So the product derivative of 1 will just be 1. In our normal derivative case, product derivative of 1 would have been 0. So but here 1 is just 1. It's kind of different. And product derivative of e to the power x ln of k is just k. Yeah, you have to go inverse. But now we might want to find derivative for any expression, not just for the results that we have found out. We might want to calculate product derivative for any expression. So how to do? So in that pursuit, we also find out what product derivative is. Okay, now let's try to find what product derivative is. Okay, now we know that product integral of f of x is actually equals to e to the power normal integral of f of x dx, of ln of f of x dx, sorry, ln of f of x dx. Now if this integral is assumed to be capital F of x, then if this is already capital F of x, then we can say that small f of x is just the derivative of capital F of x, derivative of capital Fx. Now let's try to find small fx in terms of capital Fx. Okay, now we can use the fact that capital Fx is also equals to e to the power integral of ln of small fx dx. Now this will be ln of capital Fx is equals to integral of ln of small fx dx. Now the normal integral will go to the other side as normal derivative. and that will be ln of capital Fx is equals to ln of small fx. Now the small fx will just be e to the power derivative of ln of capital Fx. Now we can see that this fx was actually the product derivative of capital Fx. Yeah, product derivative. Forgot to write that. Product derivative of capital Fx. So we have found an expression. We have found an expression for product derivative as well. And the expression that we got over here is product derivative of f of x is actually equals to e to the power normal derivative of ln of f of x. And similarly, the product integral of f of x was e to the power integral of ln of f of x. It looks kind of same. Yeah. Okay, and now if we just try to evaluate some of the product derivatives, let's say for e to the power x, that will be e to the power product derivative of ln of e to the power x, and that will be e to the power product derivative of, that will be just x, and okay, so this is normal derivative, sorry, normal derivative, this will be normal derivative, this will be normal derivative, and that is actually e to the power 1, so that's just e. It makes sense, just like we can just multiply e x times during the Riemann product, and that gives e to the power x. If it was for c also, that would give us e to the power x. Yeah, is that it? Let us check the integral for c. The integral, product integral for c in the next page. Product integral of a constant would just be c to the power product integral of ln of c. Okay, no. E to the power product integral of e to the power integral of ln c, and that gives us e to the power ln c times x. Yeah, that's e to the power x. So since c to the power c has product integral c to the power x, so e has product integral e to the power x, and it's just that c has been multiplied many times during the Riemann product as the original definition we had. So that's why this result was there. Now I hope you got the concept of product integral and product derivatives, and these are just some fun math ideas that we have invented uh, in accordance with other ideas that we had just for the sake of fun. But turns out there can be helpful interpretations and quite good applications in other fields in the future. So that's what it was. I hope you enjoyed these ideas, and yeah, thanks for watching, and look forward to seeing you in the next videos.